Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to conclude our examination of numerical differentiation formulas, and we're going to be looking at an example where the data or the function came from an experiment, so it is data. Now, we're doing these based on, essentially, we start with the definition of the derivative, and as we get closer and closer to the point, it becomes the slope of the tangent to the curve. This is really what we're after for so many different problems. And so we have a variety of formulas that we've looked at in previous lessons on how to calculate that when we don't have a function that is easily differentiable. We want to, in this case, look at this example problem. So here's a reaction problem. We have an electrode position Z and a conversion of the reactant, so how much of the reactant actually made product, and that's going to be capital X. And these were measured and tabulated for deoxygenation of hemoglobin as a function of distance from the reactor inlet in a packed bed reactor. Now at this stage, you probably don't know what all those terms mean. But mathematically, we can still work with this. And so that's really going to be our focus. So the rate of the reaction is going to be related to the conversion as a function of the distance. So this is saying that we expect the reaction to occur faster or slower depending on the location in the reactor. In this particular case, we have R sub h is negative F sub h over A times dx dz. Now F sub h is the feed rate to the reactor. In this example, it was fed at 9 moles per second. And A is the cross-sectional area of the reactor, 5 centimeters squared. And we want to know what the rate of the reaction is at a distance that's 10 centimeters in from the entrance. And they measured at various positions in this little reactor. They measured the conversion. So it started out with none of the material had been converted, had turned into product. And by the time it left, 6.5% of the material had been turned into product. So let's now solve this. And we want to, again, use estimates for the first derivative. We can use forward differences, backward differences, or central differences. So I have entered these numbers into Excel. I just copied and pasted them. And I do find that it's very helpful to know how much trouble I need to go to by actually starting by doing a graph. So if I just do a graph, these look like they are awfully linear, don't they? So probably there's not going to be a lot of value to going to more and more precise terms, but we're going to look at a variety of different ways of doing this. Now, in the problem statement, what it said is that the rate of reaction is negative F sub h, and that was value of 9 moles per second, times the derivative, which is going to be in that spot. Right now it's going to be 0. Don't worry about it. And then divided by A, the cross-sectional area, which was 5 centimeters squared. Okay, so we got an answer of 0 right now. And what I want to do is I want to estimate this derivative. So I can use any of these formulas. And let's start by doing just the simplest forward finite difference. So this is equal to f of I plus 1, so f of sub I plus 1 is f of, and this is my I right here, so I plus 1 is this one, minus f sub I divided by delta x. And I can subtract this in my head, but we can also just put it into the formula and have it figure out delta x. But delta x is 2.5. And so this is my first derivative order delta x answer. Okay. And it came up with this right here as my answer, okay? Negative rate means that the material is disappearing, which is good because I'm wanting it to react away, so it should be disappearing. And this was my derivative. How does this change? Because remember, my delta x this time is 2.5. Okay, I'm going to use that. How does this change if I wanted to do things like look at a backward finite difference? So in this case, what I'm going to do I got those signs switched. There we go. Okay. And we see that it does make a difference in the second position. Okay. If I want to do this using order delta x squared, and again doing this for the, so this was backwards or forward. This one was the backwards. This was order delta x. This was delta x. Now then, if I want to do this order delta x squared with forward, let's look at what that does for me. So the forward finite difference says that I am going to take negative f of x plus 2 delta x's. Did I put a negative in there? I did not. All right. Plus 4 times f of x plus delta x minus 3 times f at x, all divided by 2 divided by delta x, which is 2.5. Okay. Now it happens to agree to that many sig figs. I'm just going to show you the full or a fuller set of digits here for these. Okay. And if I copy this because that part won't change, I end up with that. And I could do the same thing for the backwards finite difference, but let's look at the central. Okay. The central is delta x squared. It's not delta x squared. The central equals, okay, f of x plus delta x minus f at x minus delta x, so I'm going on opposite sides, divided by twice delta x. And I probably shouldn't have put that there. I should have put it up here. This is going to change my answer, so let me... Oh, no, it didn't. Okay. Still got B7 and B5. Good. Okay. And I can copy this over. This is order x squared. And now then let me do the 1x to the 4th. Okay, the derivative for that one is negative, parenthesis, negative f of x plus 2 delta x's plus 8 times f of x plus delta x minus 8 times f of x minus 1 plus f of x minus 2 delta x, all divided by 12, all divided by 2.5. Okay, and we are seeing that we're not getting a lot of change in there. This one is, in fact, and the reason I wanted us to look at so many of these is that this answer is, in fact, halfway between what I was getting for these two answers, right? This is halfway between. probably this is actually going to be a better answer. Now, order x, order delta x. In this case, it's 2.5. In this case, it's 2.5 squared. This means it should be worse, right? Well, what if I had changed my units? What if I had said that these were in meters instead of centimeters? Now then I would be on a scale. So we still, even though I'm going to an order delta x, it doesn't mean that it gets worse the more terms I'm doing. It's still getting better the more terms I'm adding. It's just that the presumption is that the delta x is small by comparison to x. Or in this case, it's actually z, the position of the electrode. So as I add more terms, I actually am getting to better and better answers. At this point, I'm not going to say a whole lot more about this. I think that, using these formulas on your own will give you a better sense of when is it worth the time to go to the more complex formulas. Okay. But in general, no matter what the delta x magnitude is, you are going to do better by having the more terms involved. And we're going to really address this a little bit more when we are talking in class, and we'll talk about smoothness of our data. So at this point in time, I'm going to wrap up these video lessons. In our next set of lessons, we will look at numerical integration. Thank you very much for your time.